हाँ बच्चों, ये एक और हेडिंग देख लो। क्या है ये? कंटिन्यूस चार्ज डिस्ट्रीब्यूशन। ये 3 प्रकार का होता है। फर्स्ट वन इज़ लीनियर चार्ज डिस्ट्रीब्यूशन, सेकेंड वन इज़ सरफेस चार्ज डिस्ट्रीब्यूशन एंड थर्ड वन इज़ वॉल्यूम चार्ज डिस्ट्रीब्यूशन. Take this first, linear charge distribution. Okay, as the name is linear, so linear means very much related to the length. Okay, we will see the charge distribution along a length, along a line. Maybe it is wire, maybe it is a conductor, which is only length. Suppose the length of the wire is capital L, the charge given to the wire is or conductor is Q. Okay, see just this wire, and this wire is given charge Q, and suppose the charge is positive one, and it is uniformly distributed along the length of the wire. Fine. At any point P, we want to find either the electric force, the Coulomb force, or the electric field intensity. Okay, but we don't have any direct formula to find the electric force at P due to this whole wire. Okay, we want to apply the Coulomb force, but Coulomb force is for point charges, and this is not point charge, this is the continuous distribution of the charge. Fine. So what we'll do, we will take an element, and very small element, and small element length has dl, the small element has length dl. So suppose this dl length has charge dq. Fine. So we can say, suppose the distance of this element from P is small r, and at P the test charge is capped Q naught. So the force due to this element dl at P will be very small, and that small force is denoted by, suppose, df. And what is the Coulomb force? It is 1 upon 4 pi epsilon naught q1. Q1 is the element, and q2 is the test charge, and the distance between them is r. यहाँ जो element है, we are taking that element as a point charge because element is very small, and when charge is very small, that is point charge. Okay, now we want to find the total force due to this conductor or wire at P. So that will be sum of all these forces. We will take one element here, then here, and all along the wire. So then that total force F will be sum of all these. And what is the sum? Continuous sum, and continuous sum is integration. Continuous sum is always denoted by or solved by this integration, this one. Fine. Put the value of F, df, sorry. It is 1 upon 4 pi epsilon naught. Take this q naught first, dq upon r square. Okay, take constant out, q naught upon 4 pi epsilon naught, then dq upon r square. I want to introduce here some new term, that is lambda. Okay, and lambda is called linear charge density. Linear charge density. This linear charge density has formula total charge upon total length for the whole wire or for the whole conductor. But for this element, what is the length? It is dl, and what is the charge? dq. This lambda is also equal to the charge is dq and length is dl, because lambda is always constant. It is constant for whole the conductor, and it is constant for this element. From here, find the value of dq, it will be lambda dl. It will be lambda dl. Put the value of dq here. What is this? This is q naught upon 4 pi epsilon naught. dq is what? Lambda into dl upon r square, and this integration will depend upon the condition. So this much is for this heading. Okay, similarly surface charge, surface charge distribution. What is the difference? This time the charge is at the surface. Okay, suppose any sheet has positive charge distributed all over the surface. Then we want to find the force at any point P from this surface charge distribution. Again, we don't have any direct formula. What we'll do, we will take an element, very small element, which has very small area, ds or dA, whatever. Okay, suppose the small area is what? ds. The total charge is given, again same. Okay, suppose the total charge given is q and the total surface is s of this sheet. Now because we have taken this element very small, again this element will behave as point charge. This element will behave as a point charge, and we can directly say the Coulomb force due to this point charge will be how much? 1 upon 4 pi epsilon naught q1. Q1 is the charge on the element, it is again dq, and q naught upon, suppose the distance between, this point P from the element is r. Okay, this is another point, suppose this is point, then this is the df. Now we can find the total force, and that total force again will be this integral sum of this one df, because we can take so many elements here, we will add all those forces due to different elements, and this is the formula. Now put the value of df, same 1 upon 4 pi epsilon naught q naught dq upon r square, it was there, r square. Take again constant out, q naught is out, 1 upon 4 pi epsilon naught dq upon r square. Here the term surface charge density is denoted by sigma. Surface charge density, this is called surface charge density, and as the name is, it has formula surface charge density means the charge upon area for the whole sheet and charge upon area for the element. Okay, but we are taking this, so from here take the value of dq, can you, it is sigma ds, and finally we are writing this formula q naught upon 4 pi epsilon naught, this is sigma ds upon r square. Okay, so this is the formula for surface charge distribution. Similarly you can find the formula for volume charge distribution. In short, I am explaining the direct formula. Here we will take the density as rho. Okay, rho is, will call volume, it is volume charge density, and volume charge density is what? It is charge upon volume, total charge upon volume, and for element it will be dq upon dv, dq upon dv, and the final formula will come like this. You just derive. If you won't find, then ask. Okay, 1 upon 4 pi epsilon naught, same what was there, it was sigma, now it will be rho dv upon r square. Okay, just try it. If you don't, then ask. Okay, bye.